Y'all ready for math? Y'all ready for math? All right, Mr. Berto back with another advanced placement calculus review ditto. I hope that you're, working on these things. Okay, extremely important that you're putting in work. I think this is Friday's lesson. Okay, let's see. Is this Friday's lesson? Maybe it's Thursday's lesson. I think it's Thursday's lesson right here. Either way, Friday, you do have a take-home assignment due, so make sure you download that from the website. And today we're talking about integrate the rate, day 2. Integrate the rate, day 2. Let's go to 2015. Very special year for me. It's when my first daughter was born. One of the most amazing moments of my life. One of the two most amazing moments of my life was, the day that she was born. The second, amazing moment was the day my other daughter was born. All right, so 2015 right here. She was actually born only a couple days after the AP exam, so good vibes out there. Graphing calculator. And let's talk about integrate the rate day 2 because it's so popular, a second day here. The rate at which rainwater flows into a drain pipe is modeled by R of t right here. So remember, if we integrate the rate at which the water flows into the drain pipe, we'll find out how much water flew into the drain pipe. Cubic feet per hour. T is measured in hours from 0 to 8. I think there's supposed to be a T right there. Sorry, my printer's being a piece of junk. The pipe is partially blocked. It's a crazy world out there where pipes could be partially blocked, allowing water to drain out the other end at a rate modeled by D of T equals this thing right here. So this is the rate at which the water, the pipe is allowing the water to drain out of the other end of the pipe at the rate modeled by D of T. So if you integrate the rate at which the water drains out, you'll find out how much water drained out. We know that this guy right here is your entrance rate, or your rate in, and this guy right here is going to be your exit rate, or your rate out. Oh, then they tell you 30 cubic feet of water at time t equals 0. You practice these, you can start recognizing these things. Anish Kandish, not to be confused with an Anish Kanish, which is a really good potato treat that you eat early in the morning. How could you do knish early in the morning? I could eat a steak and an Italian hero at 5 o'clock in the morning. It doesn't matter for me. Hey, part A. How many cubic feet of rainwater flow into the pipe during the 8-hour time interval, 0 to 8? And in France, they call this le joke. Because if you want to know how many cubic feet flew into the pipe, integrate the rate at which the water flows into the pipe. Okay, and that's R of t. So let's integrate R of t with respect to t. And we're going to do it from t equals 0 to t equals 8. That's the normal interval here, right? We're looking at this thing for 8 hours, but they'll mess with you. They'll say from t equals 0 to t equals 6 or something like that. So make sure you're cognizant of that. Let's input all this stuff in the calculator right now because you know we gonna need it. Entrance rate, 20 sine of, what is it, x squared over 35. Look, alpha y equals for shequis, x squared over 35. And down here, what do we got? A little cubic action, so negative 0.04 x cubed plus 0.4 x squared plus 0.96 x. Okay, so at least I have those rates right there. Remember for part A right here, I just want to integrate what's in y1. So I think a little math, 9. Integral from 0 to 8 of alpha 20 y1 with respect to x. Okay, and I get, let's see, any roundings here? Nope. Okay, it doesn't say to round, so approximately 76 point, I get 570. Units, I need units. They actually asked for how many cubic feet, so I'm going to say cubic feet. Since they said how many cubic feet, they might not actually be grading units in this problem, but always something to think about. 2 points right there, okay? That one is 2 points. Definitely a very doable 2 points. Now, is the amount of water in the pipe increasing or decreasing at t equals 3? Give them reason for your answer. 2 ways to do it. You can find out R of 3, and you can find out D of 3, and you can compare them. If the rate at which the water flows in is greater than the rate at which the water flows out, the amount of water is increasing. And if the rate at which the water flows in is less than the rate at which the water flows out, then the amount of pipe is going to be decreasing, the amount of water in the pipe. Just remember, you could think about the first derivative test. Increasing or decreasing, surely there must be some sort of test. What's increasing or decreasing? The amount of water. We don't have a function that represents the amount of water in the pipe, but we know the rate of change of the amount of water in the pipe. The derivative is going to be entrance rate minus exit rate. That's the rate of change of the water in the pipe. We care about whether that rate of change is either positive or negative at t equals 3. All right, so a little calculador over here. So a little y1 of 3 minus a little alpha 20, y2 of 3. Okay, I popped that in my calculator. I got negative 0.314. All right, so since the rate of change of the amount of water in the pipe is negative, that means the amount of water in the pipe is going to be decreasing, okay? So right here, we know that, we don't have units for it. Maybe we want units for something like this. This is the rate of change of the water in the pipe. We just did cubic feet per hour minus cubic feet per hour. We're getting back cubic feet per hour. Okay, so now we know amount of water decreasing, amount of water, aqua, decreasing because the rate of change is negative. R of 3 minus D of 3 less than 0. So similar to what we did yesterday, really not too terrible. It doesn't always show up with every little piece like this, but you'll see common, things from one problem to another. Just like C, at what time from 0 to 8 is the amount of water in the pipe a minimum? Well, surely there must be some sort of test. It's the first derivative test of the amount of water in the pipe. I don't know the amount of water in the pipe, but I know his rate of change is R of T minus D of T. And that's going to go from 0 to 8 here. So just like we did before in my calculator, that's looking like it's going to be what? Y1 minus Y2 when I graph it. Just make sure you turn off Y1 and you turn off Y2. So now we got Y1 minus Y2. Okay, the window, go from 0 to 8, same as that other problem I did in the last video. And a little zoom 0 action. And remember, this is R of T minus D of T that I'm graphing. I just need to check to see where it's above and below. Okay, and it looks like it's going to start out below. Let's go graph. Okay, and now it's going to be above. I think it's above for the rest of the way, which is great because that's our minimum that we wanted. Remember, they wanted to know when the amount of water in the pipe is a minimum. Can't see me circling that there, but I just did. I swear to it. Okay, is a minimum right there. Okay, so we know that's going to occur right here. The endpoints are both maximum, so I don't need to actually worry about those. Let's calculate some 0 here. Bug, but a bug. Bug, but a... And I get what? 3.272? I was going to say 3.271 is the first 3 digits of my phone number, but I'll put 3.72. And by the way, they just want to know at what time is the amount of water in the pipe a minimum. They don't actually want to know the minimum amount of water, so it's a little bit different from the problems you did yesterday. So min amount of H2, I'll just say water, at T is approximately 272 units. I need units, hours. And then because, remember, it's a relative minimum. How do you justify a relative minimum? By saying the rate of change is equal to 0 for that crit point and changes from negative to positive. And changes from negative to positive. So really, not a terrible problem right there. I mean, it's easier than one that we did yesterday. So hopefully not too bad for part C right there. Part D. A lot of words here, but it's not as complicated as it manages to sound. The pipe can hold 50 cubic feet of water before overflowing. Okay, so that's the max amount of water it can actually have. For T greater than 8, so this is outside our interval right here. We're only going from 0 to 8. Now they're telling us the water continues to flow into and out of the pipe at the given rate. So they identified these rates only working from 0 to 8. Now approximately they also work when T is greater than 8. Right, and then the greatest phrase in the history of the English language, but do not solve. An equation involving one or more integrals that gives the time W when the pipe will begin to overflow. You're like, what the heck is going on? Just remember, the pipe begins to overflow when the amount of water in the pipe is equal to 50. And we just want to know at what time T is the amount of water in the pipe going to be equal to 50. Here's my 50. We're going to set it to the equal to the amount of water in the pipe. At any time T, how do I figure out, and it's actually any time W in this case, how do I figure out the amount of water in the pipe? Well, obviously integrate the rate at which the water flows in, and then subtract from that the integral of the rate at which the water flows out. But don't forget that initial amount of water at T equals 0 in this case. They told us 30 cubic feet. So add to that the amount of water that actually entered. So the integral from 0 up to, I don't know what time it is that it's going to overflow. You could put a T here, but they do say W is the time. If you want to know how much water flowed in from 0 to W, integrate the rate at which the water flows in, R of T with respect to T. And then subtract from that the amount of water that flowed out, the integral from 0 to w of d of t with respect to t. And this right here, that's our equation, okay? If you were actually to solve this, you would get that w value right there. It said an equation involving one or more integrals. Remember, you could always just actually combine these two integrals over subtraction, which is actually really cool. A lot of people like to do it this way. Just don't forget these parentheses with the dt. It's the same exact thing. Okay, so or, because this works as well. This is really fundamental theorem. This is great. This is the amount of water there at t equals 0. You want to know what the heck was the change in the amount of water in the pipe from t equals 0 up to t equals w. And to get the change of water in the pipe, integrate the rate at which the amount of water in the pipe changes. Okay, something that we spoke about all the way up here. So these integrate the rate problems, they definitely seem a little filthy, but they're not as bad as you might think. Some of them are filthy. Some of those homework problems, the 2008 problem, it's weird. It's a little bit different from other problems that we do. I don't think it was 2008, actually. 2010, the one where she's shoveling the snow. It's a weird algebraic part, but try to understand, you know, maybe you can't do part A, maybe you can't do part B, but maybe C and D are slam dunks. You'd be surprised. And if they use your answer from part A or part B, make up an answer from part A or part B and use it in C and D. Just keep practicing, okay? I don't care how hard you think this is. By the way, it's immensely hard. It's advanced placement calculus. But I don't care how hard you think it is. Keep working, and you will do well on the AP exam. 2011, the year that I purchased my automobile. A 12, do you know what movie that's from? A 12,000 liter tank of water is filled to capacity. Cool. At time t equals 0, water begins to drain out of the tank at a rate modeled by R of t, and it's a piecewise function from 0 to 5 hours. This rate is the rate at which the water is draining out, and from 5 hours up to whatever, this is the rate at which the water is draining out. And that's an exit rate, right? And they never give you the entrance rate, but they do tell you that the 12,000 liter tank of water is filled to capacity, and t equals 0 is when the whole, you know, shindig starts going down here. That's a hidden and niche condition, okay, to start with 12,000 liters of water at t equals 0, and now they just give you an exit rate or rate out. You know, if you integrate the rate at which the water drains out, you'll find out how much water drained out. You know, the change in the amount of water that drains out, that's how much water drains out. And you're like, yeah, I'm all ready for integrate the rate. And then they throw this bomb at you. Is R continuous at t equals 5? What? Continuity? And they do stuff. They mix stuff like this up all the time. Your AP exam, continuity. Yeah, I think it's pretty likely it's going to be on there in a part 2 problem. Very popular way to get limits involved. Probably either that or L'Hopital's rule. Talk about it when we need to. Remember, a function r would be continuous at t equals 5 if there's no difference between the y values that r is approaching and the y value that r ends up at. Remember, the y value that r is approaching, that's the limit as t approaches, what is this, 5 right here, of r of t. That's the y value that r is going to be approaching. As t gets infinitely close to 5 from the left and from the right, there's supposed to be an r. And we want to see if that's the same as the y value r actually gets to at t equals 5. Okay, so remember, that's continuity right there. This is what would have to be true for r to be continuous at t equals 5. So is it, you know? And the first thing you should do is the limit. When t approaches 5 for r of t, if you approach from the left, r of t looks like this rule, and if you approach from the right, r of t looks like this rule. So remember, there are two sides to every limit. The limit as t approaches 5 from the left-hand side of r of t. That would mean that you're less than 5, so 600t divided by t plus 3. Is it equal to, like a little question mark, the limit as t approaches 5 from the right-hand side? If you approach 5 from the right, 1,000 e to the negative 0.2t. Remember, r of 5 needs to exist, which it does. It's included right here. So you can figure out what it is, but in a second. But the limit also needs to exist. And even if you put r of t here and r of t here, you'd be all right. You don't need to write the rules. But just something to think about here. If you actually want to split this up in your calculator, you know, maybe y1, I'll put in top dude right there. So alpha y equals fasciques. Instead of 600t is going to be 600x over x plus tree. Okay, and down here we got 1,000, number of dates I have this weekend, e to the negative 0.2t, so negative 0.2x right there. And look, you just want to plug in, you know, plug in the 5 to top dude, plug in the 5 to bottom dude. So that's really y1 of 5, and that's 375, kind of cool. Could have just plugged it in probably by hand. Yeah, not so terrible there. But if you have a calculator, use it. Don't abuse it, but use it. And now I'll put y2 instead. Okay, and I end up with something that's not the same, 367.879. This limit does not exist. If the limit as t approaches 5 of r of t does not exist, this thing cannot be continuous at t equals 5. Remember, continuity is not just about the limit existing. It's also about the limit existing and equaling where the function ends up. But in this particular case, is r of t continuous at t equals 5? So r is not continuous at t equals 5 because the limit as t approaches 5 of r of t does not exist. Or you could say the left-hand limit as t approaches 5, now equal to the right-hand limit as t approaches 5. Lots of different ways to write it. So they'll have weird stuff like that in problems. Just like part B, which they won't have on your AP, but we'll talk about it in a second. Find the average rate at which water is draining from the tank between 0 and 8. And it is average rate of change. You know, it's actually the average rate of change of the amount of water in the tank, but they never gave us the function that represents the amount of water in the tank. You could get it if you want to and use the average rate of change formula on that. But when you see the word average here, and they want the average rate at which water is draining from the tank, and we know the rate at which water is draining from the tank, it's right here, it's r of t. I just want the average y value, so I don't know if you could see any of that, the average rate at which water is draining from the tank. I have the function that represents the rate at which water is draining from the tank. That's r of t right there. You just want the average value of that function. Average value is not going to be on your AP, so you won't really have to worry about it, but you still need to know it for the future. 1 over b minus a, so 1 over 5 minus 0. Integral from a to b, 0 to 5, or whatever the heck you want the average value here. Here we want the average value of the function that represents the rate at which the water is draining out of the tank, because I want the average rate at which the water is draining from the tank. This, you know, and you might be like, it's not in the AP, so what do I care? This is something that could be on the AP, not because average value, but because it's splitting the integral up over here, okay? If you actually want to do this integral in your calculator, you need to split it up. You got to go from 0 to 5. Then you got to go, is it just 0 to 5? No, it's 0 to 8. Sorry about that. So 1 over 8 minus 0. Integral from 0 to 8. What do I know about? So this is 1/8 over here. Now for this integral, first you want to go from 0 to 5 because r of t is 600t over t plus 3 with respect to t. Remember, you can split up any integral as long as the first integral starts with the lower bound, the second integral ends with the upper bound, and these two numbers match. Okay, so now our 1000 e to the negative 0.2t with respect to t. And something you might have to do on the AP, you might actually have to break up an integral this way if it's a split function. Sometimes you got to integrate these by hand. Not in this case. Okay, let's go for a trusty, hopefully not too dusty, graphing calculator. Here's my 1/8, parenthesis, little math niner. Integral from 0 to 5 of what I have in y1 with respect to x, and then plus, little math niner, integral from 5 up to 8 now of whatever I have in y1. And don't forget to close those parentheses. Okay, and I looks like I'm going to get 307.661. Why is that different from the answer that I got on my, oh, you know why it's different, right? Because I put a y1 in here when I should have put y2. So my apologies there. All right, 258.053. Okay, and look, the average rate at which the water is draining from the tank, they want units here, okay? It's the average of the rate at which the water is draining from the tank, and the rate at which the water is draining in the tank is liters per hour, so this is going to be in liters per hour. Is lit. You know, a lot of people are like, wait, if you integrate the rate at which the water drains out, you find out how much water drained out. So that's in liters. I get it, but then you're dividing by 8 hours. That's why it's liters per hour. The splitting the integral is the important thing here. Try not to worry so much about the average value because you won't have to do it. But once again, it's always something you should think about. Part C, very similar to a problem we did yesterday or today. I don't remember already. Find r prime of 3. And then what? Using correct units. Explain the meaning of the value in the context of this problem, but you could also make it very generic. Just remember, r prime of 3, you could use your calculator, but r prime of 3, you'd be taking the derivative of top dude, right? y1 in my calculator, because 3 is in between 0 and 5. So r prime of 3, little math 8. Let's take the derivative with respect to x of y1, not y2. Evaluated t equals 3. You actually get 50. Believe it or not, you don't need to put the runoff right here. explain the meaning in the context of the problem. Remember, the second you get, if it was a definite integral you're explaining the meaning of, you start with the change in. But if it's a derivative you're explaining the meaning of, you start with the rate of change of. Rate of change of. So you write that down first. Then you're like, what the heck did I just take the derivative of r of t? What does r of t represent? R of t represents the rate at which the water drains out of the tank. So we got the rate of change of the rate at which the water drains out of tank, rate at which the water drains out of the tank. You know, make sure you put your units here in, and it's the rate of change of the rate at which the water drains out of the tank. The rate at which the water drains out of the tank is liters per hour, but we're taking the derivative of that with respect to hours. That's why it's liters per hour squared. Then don't forget to say at t equals 3 hours. It's really the end of the third hour. That's good, okay? That explains it in the context of the problem. It's the rate of change of the rate at which the water drains out of the tank. You know, what does that really mean? The rate at which the water is draining out, the rate of change is positive, so it's actually increasing, okay, the rate at which the water is draining out at the end of the third hour. You don't have to worry so much about what's going on contextually, like I said, as long as you actually say it this way, okay? So remember, make sure you know how to describe a derivative and describe an integral in your AP. I'm telling you, you're going to have it on there, okay? Everybody's moving in that Common Core direction that you know I all hate, but they love you to explain stuff like that, so get ready. Part D, write. And then, but do not solve. Greatest expression ever right there. An equation involving an integral to find the time A when the amount of water in the tank is 9,000 liters. So it's just like the last problem we did. We wanted to find out when the amount of water in the pipe was 50. I think it was cubic feet, because then the pipe would begin to overflow. Here we want to know when the amount of water is going to be 9,000. And that means you got to get the, you know, the function that represents the amount of water and actually set it equal to 9,000. Well, remember, this thing starts with 12,000 liters of water right there. But now no water is going to be added. Water is only going to be drained out. So we're going to subtract the amount that was drained out. This is t equals 0 right here. So we'll start at t equals 0. But we'll end at this t value when the water is equal to 9,000. They actually told you to call that t value A. If you put t, you'll probably be all right. Just remember, if you want to know how much water is draining out of the tank, integrate the rate at which the water drains out. And that's our equation, okay? This tells you the amount of water at time t equals A. We want to see when it's equal to 9,000. You could put a t here, but then you have to put r of x with respect to x, so be careful. So similar to, you know, the last problem that we did right here, same type of thing. This one's a little bit more complicated. Integrate the rate. They've been pretty traditional lately, okay? There are some integrate the rates with graphs, okay, and sometimes with tables. We'll get there eventually. You'll see it in your homework as well, but tables kind of filter into the curriculum a little bit later. There's one, I think, tonight for homework with a graph with an amusement park. It's difficult, okay, because it actually tells you the rate at which people actually move onto a ride. And then they tell you the rate at which people get on the line. And the rate at which people move onto the ride is actually the rate at which people are exiting the line. So that's my little hint for that problem tonight. And I hope you guys are working on this. Don't slack off. You know, I know you got 100 things going on. You're stressed. Like I said, if you got that major stress going on in your life, if people are, you know, are not well or something, I get it, okay? But math can work as a great distractor when you want to get your mind off of things. Focus on this stuff, okay? If you want to do well in the AP, you got to work. If you don't work, you will not do well in the AP. I don't care who you are, how well you've been doing. You won't. Trust me. I've seen it happen before. So please put in your work. Do the best you can. As always, stay healthy. Stay safe. You know, we'll talk more about how you're going to have to upload your questions to the AP exam. I'm not even supposed to go through that with you, I don't think, but I'll do my due diligence as much as I can so we know what's going on there. And I know you seniors are like, oh, my prom, my graduation, this and that. I get it. It's a terrible time for this to happen to you, and I really cannot tell you how horrible I feel for you because of something like that. But life goes on, okay, and you'll see in your life things like this will happen, okay, and you got to persevere. You got to get through them, and you all can because you're amazing and wonderful people. So stay healthy, stay safe, and we'll see you next time. Adios.